this question, how to estimate the area under the curve. So I'm going to write it this way. Integral from -2 to 2 of 4 minus x squared dx. And again, all that says is the area under f of x equal to 4 minus x squared on the interval from -2 to 2. Right, it's a lot less writing to write this than it is to write this, but they mean the same thing. Okay, so estimate this area. What was the question here? Using either n equals 2 or n equals 4 subintervals with midpoints. So I will draw a picture, but let me just kind of, we know the form, or we should know the form of this at some point. I know, so let's do n equals 2. Probably not sure. So 4 minus x squared, the downward opening parabola looks like this. Specifically, we're trying to estimate this area. So I'm using 2 subintervals. So for n equal to 2, the width of my subinterval, which we usually call delta x, is my total length, which is 2 minus 2 divided by 2. That's 4 over 2, which is 2. No surprise, right? If this is the total length, we're going to have 2 rectangles. One of them is going to be the rectangle of this base, one of them is the rectangle of this base. And for each of these rectangles, we're going to use the midpoint as the height to find the height. So the midpoint between 0 and 2 is 1, between -2 and 0 is -1. So we're using that point to find the height. Same deal here. So those are our 2 rectangles with n equals 2, using the midpoints to find the heights. Get that the area, and so I guess this is going to be the midpoint approximation using 2 subintervals. That's going to be my base times my height plus my base times my height. 2 times f of -1 plus 2 times f of 1. Or more generally, maybe, yeah, or written more compactly, I could say it's the sum from from k equals 1 to 2 of 2 times f of, let's see, when k equals 1, I want -1. So I'm going to do 2k minus 3. Right? When k equals 1, 2 times 1 minus 3 is -1. When k equals 2, 2 times 2 is 4, minus 3 is 1. So I get f of -1 and I get f of 1. You probably wouldn't write this one as a sum because it's only 2 pieces, but you could. So let's see, that's going to be, let's see, f of -1. My function is, I didn't actually write down the function. The function is this function here, f of x, which is 4 minus x squared. F of -1 is going to be 3. And not surprisingly, f of 1 is also going to be 3. It looks like those rectangles have the same area. They do. That's going to be 12. So our estimate using 2 rectangles is going to be 12. Let's do the estimate using 4 rectangles and midpoints. So now we're breaking this up into 4 equal subsections. So in fact, let's erase this here. So now we're breaking this into 4 equal subsections. So the width of each subinterval is going to be 1, right? It's going to be, our delta x now is going to be 4 divided by 4, which is 1. So we're going to get 1 as the base. In fact, let me actually, I want to write this kind of the other way. So what I'm really going to do is I'm going to write this as the sum from k equals 1 to 4 of f of some x value that depends on what k is times by delta x. Or as I want to say, base times height. So the bases are all going to be 1. Right, the base for this rectangle is 1. The base for this rectangle is 1. Sorry, let me draw there. And we're using the midpoints. So these are my 4 intervals I want to estimate the areas of. And for each of them, I'm going to use the midpoint. So for this one here, I'm using the midpoint. This one here, I'm using the midpoint. For this one here, I'm using the midpoint. Should be the same height. And for this one here, I'm using the midpoint. So those are my 4 rectangles I'm going to use to estimate the area of this. Now, the midpoints are halfway between all the endpoints. So like this midpoint is positive 1/2. This midpoint is positive 3/2. This midpoint is negative 1/2. This one's negative 3/2. So we could think of when k is equal to 1. So basically, each of these are going to add 1 each time. So I'm going to do f of, I'm going to add 1 each time. Well, k is increasing by 1 each time. So it's going to be just k plus or minus something. When k is 1, I want to get negative 3/2. So I need to do k minus 5/2. Right? If k is 1, 1 minus 5/2 is negative 3/2. If k is 2, 2 minus 5/2 is negative 1/2. If k is 3, 3 minus 5/2 is 1/2. And if k is 4, 4 minus 5/2 is 8/2 minus 5/2, which is 3/2. So this does give us what we want. Now, I'm not saying you need to write it this way. I'm just trying to show you like how you would get from saying we know that we want 1 times f of negative 3/2 plus 1 times f of negative 1/2 plus 1 times f of 1/2 plus 1 times f of 3/2 into something a little more compact. And the way you would do it is to write it like this. Now, you can start at k equals 1, you go to 4. You can also start at k equals 0 and go to 3. And do f of, instead of k minus 5/2, it would be k minus 3/2. Either way, you're still calculating this thing here, which is just going to be, let's see, it's going to be f of negative 3/2. So that's going to be 4 minus negative 3/2 squared, which is 9/4, plus 4 minus negative 1/2 squared, which is 1/2. Sorry, 1/4. And then we could write the other ones, but we could also recognize that f of 1/2 is going to be the same. And f of 1/2 is also going to be 4 minus 1/4. Great, I have 2 of those. And f of 3/2 is also going to be the same as f of negative 3/2. So great, I have 2 of those. So I get 8 minus 9/2 plus 8 minus 1/2. I end up getting 16 minus 10/2, which is 60 minus 5, which is 11. So that's my better estimate. And the more rectangles we use, the better our estimate gets. So we could use 8, we get a better estimate, et cetera, et cetera. So Daniel, we were just using some number of rectangles, in this case 4 rectangles, to estimate the area under the curve f of x equal to 4 minus x squared. We use 4 rectangles and we use midpoints. And I think this might have been a homework problem or similar to a homework problem. Okay, let's do another one. A couple of different people sent me this one, which is similar. So one of them was from 1 to 9, one of them was from 1 to 25. Let's go ahead and do, I'm going to split the difference. Let's say I want to estimate the average value of the function f of x equal to 1 over x on the interval from, let's do 1 to 13. What's 13 really, James? 1 to 13? 13 is terrible. Let's pick something else. 17, 25 is kind of a good choice. I'm not going to lie. 5, we'll pick 25. The other possible choice is 9. 9 is not good. So estimate the average value of this function on this interval using 4 rectangles with midpoints. Okay, so here's the thing about average value. It's very easy to calculate. If you want to find the average value of a function over an interval, it's just the area under the function divided by the length of the interval. So, for example, for this function, 1 over x, it looks kind of like this. Let's say here's 1 and here's 25. And let's say we found the area. So that area there, whatever it is, let's say we got it. Well, then the average value would just equal whatever that area is divided by the length of the interval. And there's a couple ways of thinking about this. One way of thinking about it is you're essentially finding, if with this picture, what the average height of this function would be. So if you took that same amount of area and shook it all out so that it was even, but still the same amount of area, the height that it was at would be the average height. What you're kind of doing is you're saying, I want to take, right, the same amount of area. Let me just draw it here. Which is, it's going to be maybe, let's say this was the average height. So what you're saying, if this is the average height or average value, is that this area under this rectangle is the same as this area, this black area that we calculated here. Same base, but all of this is the same height, whereas all the area in black is not. Another interpretation, which I think is worth thinking about. So because someone asked me, what does average value actually mean? And I kind of had to think about it, and it's kind of dumb to, when you get back to it, it actually literally means the average value of the function. But it's kind of like, well, James, I know you're just saying the same words again. So it's maybe a little easier. It's actually, oh, this is, I'm gonna take it back to the airplane problem. Yeah. It's gonna be kind of dumb because you're gonna, well, it's actually, no, it's gonna be good because you're already gonna know the answer. So for the airplane problem, I'm just gonna look at the first half of it, the first part, where the airplane goes from 0 kilometers per hour to 50 kilometers per hour in 10 seconds. Great. And I know I talked about this before. This is like 0 kilometers per second. And this is, oh, I forgot what it was. I think it was 1 over 72 kilometers per second. That sounds right. So we divide by 3,600. Let's see, 50 over 3,600, 5 over 360. Yeah, that's 1 over 72. 1 over 72. Yeah. Cool. So I want to find the average speed of the plane. Well, here's something that's kind of nice. If you accelerate constantly, you know that the average speed is actually just the average of your beginning speed to your end speed. That's a true thing. But we can also actually use it to calculate the average value. We can use what we're doing over there to calculate the average value function. So to find the average value, I'm going to do this. So from 0 seconds to 10 seconds, the plane goes from, right, this is time measured in seconds. This is velocity measured in kilometers per second. So from 0 seconds to 10 seconds, we go from 0 kilometers per second to 1 over 72 kilometers per second. Okay. So again, right, this is the velocity, and we know that the area under the curve represents the distance traveled or the displacement. Well, the area under the curve, which you could totally write as the, oh, I guess I didn't write the velocity function. The velocity function here is 1 over 72 t. 1 over 720 t. So, right, when t equals 0, you get 0. When t equals 10, you get 1 over 72. Okay. So then if I want to find the area, you could just calculate the area using the area of this triangle. Right, one way to do that would be, okay, James, it's 1/2 base times height, which is 1/2 times 10 times 1 over 72, which is going to be, let's see, 5 over 72. That would totally work if you know what the area of the geometric shape is. Or you could say, James, I know how to do integrals and stuff. It's going to be obviously the integral of velocity from 0 to 10. So if you integrate 1 over 720, t over 720, not 1 over 720. You get t squared over 2 times 720 from 0 to 10. Plugging in 10, you get 100 over 2 times 720. But cancel a 0 there and a 0 there. 10 over 2 is 5. Oh, look, you get 5 over 72. Great. So that's how far we traveled. We traveled 5 over 72 kilometers, right? We were going kilometers per second, time a second, so we've traveled 5/72 of a kilometer. Okay. So if I wanted to find the average velocity, I could take the distance I traveled, 5 over 72 kilometers, and divide it by how long it took me, 10 seconds. So my average velocity, which is the average value of this velocity function, right? This is my velocity function. V of t is 1 over 720 t. My average value is, well, it's 5 over 72 kilometers divided by 10 seconds, which is exactly 5 over 720 kilometers per second, which is, yeah, our average speed, which I will point out in this particular example is the average of the beginning and the end, because again, it's a constant acceleration. That's not always the case, right? If you want to find the average speed of something, it's not always just the average of the beginning and the end, but it happens to work out here. Let's see. The average value of a positive function over given by the area. Yeah. Oh, okay, it's a question. Sure. That's exactly the question we're doing. I'm sorry, I do not know how to pronounce your name. Person who sent me a direct message. But yes, that's the question we're working on the other side, just with a different number. I used 1 and 25, and I used a slightly different function. But so I just want to make sure everyone's really, really clear. Average value literally means whatever function you're dealing with, right? This function that's representing velocity. If I want to know, if I know my velocity is increasing or changing over some interval, I can take the integral of it, divide by the length of the interval, and I can tell you what the average velocity is of that function, or in general, the average value of that function. Now, in real life, it's a super straightforward calculation. If you know how to find the area under a function, you know how to find the average value, because you're just taking that area and you're dividing it by the length of the interval. So here, we're going to estimate the area under the curve 1 over x. 1 over x? Yeah, that's what I was thinking. And then we're going to divide it by the length of our interval. And I'm going to use 1 and 25 instead of 1 and 17, but same idea. So to estimate the area, we're going to use 4 rectangles with midpoints. So I still like to draw a picture, even though we totally don't need to, but it's still worthwhile. So here's my picture, and here's 1, and here's 25, and I'm going to break that up into 4 equal length subsections. So my delta x, the length of each subinterval, is my total length divided by 4, which is 24 over 4, which is 6. So 1 plus 6 is 7, 7 plus 6 is 13, 13 plus 6 is 19, 19 plus 6 is 25. So these are the regions I'm trying to estimate the areas of, here, 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 and here. And again, we're using midpoints to do that. So I have to take the midpoint of each subinterval, So the midpoint of 1 and 7 is the average of 1 and 7, which is 4. And the nice thing is, if you know how far apart the endpoints are, you know how far apart the midpoints are. So instead of finding the midpoint of this, the midpoint of that, the midpoint of that, you can say, oh, well, these are 6 apart, so these are 6 apart. 4 plus 6 is 10, 10 plus 6 is 16, 16 plus 6 is 22. And I'm going to use those midpoints plugged into the function to estimate the area of each rectangle. Okay, my rectangles don't look great, sorry. So we're going to approximate the area under the curve with 4 rectangles using midpoints, and that's just going to be f of 4 times 6, right? Height times base plus, let's just factor out the 6. We know what we're doing. So it's f of 4 times 6 plus f of 10 times 6 plus f of 16 times 6 plus f of 22 times 6. So our approximation for the area is M4. So that's what we're approximating the area with. That's going to be 6 times 1/4 plus 1/10 plus 1/16 plus 1/22. And I do not recommend, I don't really recommend doing that. No, really. I would probably get a calculator. Let's see what happens if we use the calculator. 1/4 plus 1/10 plus 1/16. This might not be terrible. Plus 1/22. That looks pretty terrible. Let's see, will my button that changes fractions, decimals, and back help me out here? Yeah, it did. Awesome. So sometimes your calculator, if you're lucky, will change a decimal to a fraction. It's 403 over 880. So this is 6 times 403 over 880. We can cancel a 2 there and a 2 there. So we get 3 times 403, so we get 1209 over 440. But we're not done, because, so that's what we're approximating the area to be. And then the approximate average value is approximately our area approximation divided by the length of the interval, which is 24 in this particular example. So that's going to be 1/24 times 1209 over 440. Let me go back actually, because I think I can make this a little bit simpler. I'm going to write this as what it was before, as 6 times 403 over 880, because maybe it would be just smarter to say, oh, I can cancel a 6 there with a 6 there. Again, these numbers are kind of dumb, but that's what we got. So we get 403 over 4 times 880, which is 3,200 plus 320, so 35, 20. I don't think that simplifies. But the whole point of this is just that if you know how to calculate or approximate the area, you know how to calculate or approximate the average value. It's dividing whatever you got by the length of your interval. Cool. Average value comes up every once in a while, but it's not a huge deal. I think I heard someone about to ask a question though.
Yeah. So is it more favorable to always use midpoints, or is it depending like from situation to situation?
So here's my two-pronged answer. In general, midpoints do give a better estimate of the area. So if you're actually using midpoint, if you're actually just estimating, then yeah, midpoints are probably preferable in that they give a better approximation. Actually, I have 3 things to say. 2, it's usually easier to do the calculation if you use left or right endpoints, because just the process of having, you're already finding the left and right endpoints already, and then finding the midpoints is an additional step. So if it were up to me, I would probably use right endpoints because it's one less thing I have to do. Also, what we're really going to do with this is use this, in fact, that's what we're about to start doing, is use this to then take a limit of it to find the actual, not approximated, but literally true area under the curve. And what's nice about this is mathematicians have proven many, many, many times over that it doesn't matter if you use left endpoints or right endpoints or midpoints or upper sums or lower sums or any point in the interval, right? You can use a point that's like 2/3 of the way over, right? Or they can all be different, right? You can have like one that's a midpoint, one that's a left point, one that's a right point, and as long as you're picking some point in the interval for each interval, mathematicians have proven that once you take the limit of that expression, you get the same value no matter what you did. So what that means, we can make the choice that is the easy choice, which is using the right endpoints. Because that's the choice I'm going to make. And it's the choice that you're making in your homework. For a couple problems, it just is phrased differently, but it still ends up being the right endpoints. So let's look at some examples of that. Yeah. So let's start off with a really easy example. Fairly easy. So we're actually going to calculate the area under the curve f of x equal to 2x plus 5 on the interval. I think from -1 to 3 is what we usually like to do. It's fine if it's something different, but because they're easiest, Daniel, to be perfectly honest, they're the least calculation intensive. And I'll show you both if you want, but you're going to see that, yeah, maybe I'll try and show you both with this one. It's a little bit of a pain in the butt, I'm not going to lie, but it might be worth our while. So let's see. Yeah. Okay, sure. I'm just looking at one thing here. We're good to go there. Yeah, okay, sure. So, yeah. So I want to calculate the area under this curve on this interval. And so first we're going to start by approximating it. So I'm going to do this. Let's see, so -1, sure. Probably need all that room. Looks vaguely like this. Probably looks actually steeper than that, but I'm trying to even draw it so that we can see it. So we're trying to find this area. And we're going to use rectangles. I'm going to use, so the way, at least the problem in Schulten's class on the homework is phrased is, for some function, decide whether you want to use the left endpoint or the right endpoint so that you get an upper sum. So let's say, so I'm going to try and let me actually look at that question real quick, just so I'm going to try and phrase this one a little bit more like the Schulten's question, just so those of you that are doing that one have kind of an idea of what's going on here. So the first part of the question is, let's see, where'd you go? Yeah. So they really break this one down. So divide the interval into n intervals of sorry, I can't even read. Divide the interval into n subintervals of equal length. How long is each interval? So the total interval length is 4. So our subinterval length, which again I typically call delta x, is our total interval length, 3 minus -1 divided by n, which is 4 over n. Okay, the second part of the question is, in order to determine an overestimate for the area under the graph of the function, at what x value should you evaluate f of x to determine the height of the first rectangle? So, hopefully everyone can see over here. I don't know exactly how big 4 over n is because again, it depends on actually how large n is. We're going to let n get really large. Well, let's say maybe that's our first subinterval. So this is our first subinterval. So that point there, that's -1 plus 4 over n. Right? We took our starting point, -1, and we added 1 subinterval's worth of length, which is 4 over n. And now I want to, for this first region here, I want to pick the endpoint that's going to give me an overestimate. Well, since this function is increasing, the overestimate is going to be the one I pick. Is going to be given to me by picking the right-hand side, because the right-hand point is the highest point, which is going to give me that rectangle right there. That's going to be true for every rectangle in this function because the function's increasing. Right? So for the next subinterval, I would, right, let's just pretend it hits at 0. I would say, okay, well, I'm going to use that point to find the height, and there's going to be my next rectangle. So for the first rectangle, my right endpoint, which I'm going to call x sub 1, is going to be -1 plus 4/n. And for my second rectangle, the right endpoint would give me the overestimate. It would be x sub 2 equal to -1 plus 4/n twice. Essentially, every subsequent right endpoint, or endpoint that gives you an overestimate, is going to be another 4/n away. Okay, so that one's another 4/n away. So right, each time, let me see if I can make this so you guys can see it. Right here, we're starting at -1, and then we're adding 4/n, and then we're adding 4/n, and then we're adding 4, right? We just keep adding the subinterval 4/n to get the next point. So the area of my first rectangle is going to be base, which is 4/n, times the height, which is f of that first point, -1 plus 4/n. Then the next rectangle, so we're going to add, is going to be a base of 4/n times the height of f of -1 plus, well, I started at -1, now I've added 4/n twice. Plus, do it again, 4/n times, so the next rectangle, right, it's going to be the base times f of -1 plus 3 times 4/n. So that's the idea. That's how we're approximating the area. But they want us to, let's see, let me look at this question, right? Why is -1 a constant? So -1 is kind of a constant in this particular example because we're starting at -1. Right? We're doing the interval, we're calculating the area under the curve from -1 to 3. Whereas the homework problem, I think, is going to go from 0 to something, which is a little bit easier, actually. That'll be fine for here. Okay. So then the idea basically is they ask us to kind of figure out, okay, what's happening in the kth subinterval. So this is the first one. This is the second one. This is the third one. This is the kth one. So take a look. For the first rectangle, the area is base times f of -1 plus 1 times 4/n. For the second rectangle, the area is base times f of -1 plus 2 times 4/n. For the third rectangle, the area is base times f of -1 plus 3 times 4/n. So it looks like the only thing that's changing is what we're multiplying by the 4/n. So it would be totally reasonable to guess that for the kth subinterval, we're going to plug in what I like to call x sub k, which is -1 plus k times 4/n. Right? We started at -1 and we've gone literally over k rectangles. 1, 2, 3, k. Right? If you go to the right side of the first rectangle, you've gone -1 plus 1 4/n. Go to the right side of the second rectangle, is -1 plus 2 4/n, plus 3 4/n, plus k 4/n. So that's what we've got there. And then here's what we can say. The total area is what we're going to get when we add them all up. So you can write it out really, really long. Right? 4/n times this, plus 4/n times this, plus 4/n times this, all the way to the last one, right? Which would be, right? This last one, which would be 4/n times f of -1 plus 4 times, sorry, n times 4/n. which I know is just -1 plus 4, which is 3. But the idea is you're using n rectangles, so the last one should be the nth one. But there's a more compact way of writing this. I can say, hey, look, that's going to be, the area is going to be approximately the sum from k equals 1 to n of f of -1 plus k times 4 over n times our delta x. Or in less fancy mathness, your height of your rectangle times your base of your rectangle. Questions about this? We're not done, I'm just pausing to see if anyone has any questions. Okay.
James, I have a quick question.
Sure, go ahead.
After like our final rectangle at x at 3, what does that say after? Is it 1 minus
It says, -1 plus n times 4 over n.
Okay.
Which is what you get when you plug in n, right? If you plug in n, you get -1 plus n times 4 over n.
Okay.
Which is just -1 plus 4, which is just 3. So, oh yeah, the last rectangle is going to have a height of f of 3.
Thank you, James.
Cool. Good, Daniel. Glad to hear it. So now we're going to use some things we talked about last week to actually calculate this thing. So first of all, I need to actually use the function. So let me write this and this on the other side. So f of x is 2x plus 5, and we're approximating the area with the sum from k equals 1 to n of f of -1 plus k times 4 over n times 4 over n. Okay. So now we are going to, words. We're going to replace f of this with the actual function, right? So f of x is 2x plus 5. F of this garbage is 2 times that garbage plus 5. So that's going to be the sum from k equals 1 to n of 2 times all this plus 5. So 2 times -1 plus, I'm going to write this as 4k over n. So it's a little easier to handle. Plus 5, all of that times 4 over n. Okay, we want to simplify this. And what I mean by simplify is we basically want to add stuff together, distribute the 4 over n, and then break it apart. So let's see, that's going to be the sum from k equals 1 to n of -2 plus 8k over n. I'm distributing the 2 plus 5 all times 4 over n. And then that's going to be the sum from k equals 1 to n of, let's see, -2 plus 5 is 3. And 3 times 4 over n is 12 over n. And then 8k over n times 4 over n is going to be 32k over n squared. Here's a helpful tip. When you're doing this kind of problem, when you get to this step where you kind of simplify this, you should always have fractions where the power of n is 1 larger than the power of k. N squared, k to the first. N to the first, k to the 0th. Great, I'm in good shape. So now here's what we're going to do. We're going to break this apart into, this is why we talked about the rules of summations last week. We're going to break this into 2 summations. So it's the sum from k equals 1 to n of 12 over n plus the sum from k equals 1 to n of 32k over n squared. And the last thing we're going to do before we finish it, well, the next thing we're going to do is we're going to factor out the constants. So the things that are constants are not k. Right? K is changing. K is 1, and then 2, and then 3, and then 4, and then 5, and so on. But 12 and 32 are constants, and n is actually considered a constant in this context. Right? N is just whatever the last number you're getting to is. Could be a million, but n isn't changing. Right? N is just set to be whatever the value is, and then yeah. So we can write this as the factor out the constant 12 over n times the sum from k equals 1 to n of 1. And factor out the constant 32 over n squared times the sum from k equals 1 to n of k. Sorry. Okay, we're almost there. Now we have formulas for these things. The sum from k equals 1 to n of 1 is just n, right? It's 1 plus 1 plus 1 plus 1 plus 1 n times. And the sum from k equals 1 to n, right? So 1 plus 2 plus 3 plus 4 plus all the way to n. We saw last time that that was equal to n times n plus 1 over 2. That's why we need these formulas. You can simplify this, but you really don't need to. So now here's what we're going to say. The actual area is equal to the limit as n goes to infinity of this expression of the sum from k equals 1 to n of f of x sub k times your delta x, which is what this is. And then we did all this work. So it's equal to the limit as n goes to infinity in this particular case of 12 over n times n, that's just 12, plus 32 times n plus 1 over 2n squared. So I'm going to get 12 plus what? So what's the limit of this expression here? Anybody have a guess?
Half, 32 divided by 2.
Right, 32 divided by 2. And the reason that's true is because if you look at this expression, right, that's a 32n squared plus 32n over 2n squared. And we take the limit of a rational function as n goes to infinity, you get the quotient of the leading coefficients, which is 32 over 2. So we get 28. That's the actual area under this curve. Kind of great. So let me just mention a couple things. One, we could have totally calculated this area using geometry, which is fine. In fact, let's go ahead and do it just to verify. Do I want to do that yet? Yeah. Actually, before I do that, let me point out how using left endpoints would be worse. So yeah, let me just do that real quick. So you can do this using left endpoints, and here's the difference. If you use left endpoints, which would be lower sums, right? Because that would give you an underestimate every time in this particular example. Not always, just this example. If you use left endpoints, you're going to now calculate the area under your curve as, so you're still adding up all the rectangles. And for the kth rectangle, instead of using -1 plus k times 4 over n to plug into the function to get the height, you're going to use this one right here, which is 4 over n less. So it's f of -1 plus k times 4 over n minus 4 over n times your delta x, which is 4 over n. That looks worse, right? Instead of plugging in this thing into my function, now I have to plug in -1 plus k times 4 over n minus 4 over n. Or if you prefer, f of, let's see, -1 plus, you can factor out the 4 over n and have a k minus 1. That seems less good. Or if you want to do midpoints, is even worse, because for midpoints, That's an n, sorry. You would have to average these 2 points, right? So you would take the average of those and plug that in. So it would be f of the average of this and this, which is really terrible, right? It's this -1 plus k times 4 over n plus this -1 plus 4 over n times k minus 1 all over 2 times 4 over n. And then you have to right, plug that in, right? That looks, I mean, you can probably simplify this a bit, but it's going to be gross. So that's the whole idea, is that you could use left-hand points, you could use midpoints, you could use other crazy points, but the nicest points to use are the right-hand points, because they're just the easiest to write out what each of the next values you're plugging in is. So that's what we usually prefer to do. As far as the geometry of this, let's draw this picture again real quick. So you can either use the trapezoid formula, which nobody remembers, or you could just break this up into a rectangle and a triangle. So there's my rectangle. So the rectangle has a base of 4 and a height of, let's see, if I plug in -1 to my function, which was my function 2x plus 5, I think. That sounds right? Yeah, 2x plus 5. So plugging in -1, 2 times -1 plus 5 is 3. So the height of this rectangle is 3. And that's going to be 12. And then my triangle, well, the area of the triangle is 1/2 base times height. The base is 4. And the height is, let's see, the height of that triangle is, I know if I plug in 3, f of 3 is going to be 11. So I know that this point here is also at a height of 3. So that height between them is 8. So I get 1/2 4 times 8, which is 1/2 of 32, which is 16. And you add those together, oh yeah, you definitely get 28. So in this particular example, we could totally just use the fact that we know how to find areas of rectangles and triangles to see that the area is also the same thing. So let's do another example. We'll do another example, and then we'll take a 5-minute break. So let's do one squared. So let's say, and I'll do one similar-ish to her homework problems. Let's do that. Sorry, where'd you go here? Yeah, let's, okay, pick gross numbers. Fine. So consider the function f of x equal to, I'll pick something. Let's do 4x plus 3x squared. Sure. On the interval from 0 to, let's get not too crazy. Let's go 0 to 5. 0 to 5. Sure, why not? Okay. And we want to do all the same stuff to approximate the area. So I'm going to try and do it a little bit faster. I know, and so I should point out, right, that this, no, that's fine. This function, 4x plus 3x squared, has x-intercepts at 0 and -4/3, I think, right? Factor out an x. Yeah, -4/3 and 0. So it looks something like this. And all I really care about is that the interval I'm working with, it's increasing. So I'm going to draw it kind of exaggerated. Here's my parabola, right, from say 0 to 5. And I'm trying to find the area under that curve. So again, I'm going to do the same thing. I'm actually, here's what I really want to start with. We're trying to find this. The limit as n goes to infinity of the sum from k equals 1 to n of f of the thing you're plugging in to find the height. And I forget how they're phrasing here. I just want to make sure. Yeah. Sure. F of, we usually call it x sub k. This is the x value in the kth interval that we use to determine the height. It could be the left endpoint, it could be the right endpoint, it could be the midpoint, it literally could be anything. I'm going to use the right endpoint because that is the easiest way to do it. It's also what would be right for this problem if you're looking for overestimates to start off with. And then we're going to multiply by delta x, which is just the width of the subinterval. Okay, Kat, you can leave if you want to leave. Be my guest. Go away. There we go. So we need to identify these three things. Well, we know what our function is. Our function is just 4x plus 3x squared. We need to find our delta x, which is 5 minus 0 over n. And we need to find the right endpoint of the kth subinterval. So for the first subinterval, the right endpoint is 5 over n. So x sub 1 would be 5 over n. For the second subinterval, well, I'd add another 5 over n. So it would be 2 times 5 over n. And you might have guessed, for the third subinterval, the point we're going to plug in is going to be 3 times 5 over n. So every time we move over, we're just adding another 5 over n. We're increasing the multiple 5 over n. So this is also, why not 2 plus 5 over n? Because we're not integrating from 2 to 5. We're integrating from 0 to 5. Or do you mean why not 2 plus 5 over n to get the next one? So the reason why is because I'm going to erase this here, because each of these intervals have the same length. So this length here, and let me just load it up. Right, this interval has a length of 5 over n. 0 plus 5 over n is 5 over n. This interval has a length of 5 over n. 5 over n plus 5 over n is 10 over n, or 2 times 5 over n. This interval has a length of 5 over n. That point's going to be 3 times 5 over n. And so we're using these points to find the heights. So, sorry, not that one. So using this first point to find the height there. Using this second point to find the height. Using this third point to find the height. If we want overestimates. So for the kth subinterval, and this is the first one, this is the second one, this is the third one. For the kth one way out here, right? The right-hand endpoint of that kth subinterval is k times 5 over n. Right? The first one, the right endpoint is 1 times 5 over n. The second one, the right endpoint is 2 times 5 over n. The third one, the right endpoint is 3 times 5 over n. So we kind of see the pattern. Oh yeah, for the kth one, first, second, or third, fourth, the right endpoint is k times 5 over n. And if you hated yourself and you want to use left endpoints, the left endpoint would be k minus 1 times 5 over n. Or if someone was asking to use left endpoints because they didn't like you very much. Don't use left endpoints unless you have to. So what we're going to see is that we're going to plug in that for our x. So when I write this limit, it's going to be the limit as n goes to infinity of the sum. So my function f of x is 4x plus 3x squared. F of, oh, I forgot to write what x of k is, which is k times 5 over n, which I'm just going to write as 5k over n. I'm going to do f of 5k over n times my delta x, which is 5 over n. And then we're actually going to plug that in. So f of 5k over n is going to be 4 times 5k over n plus 3 times 5k over n squared. This is going to be limit as n goes to infinity of the sum. I forgot the k equals 1 to n from k equals 1 to n. If someone doesn't write that, they usually mean that. Of 4 times 5k over n plus 3 times 5k over n squared times 5 over n. And now we're going to simplify it. So let me write that on the other side. Let's see, we've got the limit as n goes to infinity of the sum from k equals 1 to n of 5 times 4k over, that's not right, 4 times 5k over n, sorry. Plus 3 times 5k over n squared times 5 over n. Great, let's take a look. That's right. Okay, let's simplify. So let's do kind of two things at once. 4 times 5k, that's not. 4 times 5k over n is 20k over n. 3, so 5k squared is 25k squared. Times 3 is 75k squared over n squared. So I squared this and got 25k squared over n squared, then multiplied by 3, so 75k squared over n squared. And then I multiplied all of that by 5 over n. That's going to be the limit, as n goes to infinity, of the sum from k equals 1 to n. So now I'm going to distribute this 5 over n to each of those terms. So 20k over n times 5 over n is 100k over n squared. And 5 over n times 75k squared over n squared is 5 times 75 is 375 k squared over n cubed. And I will point out again that we're in good shape because each fraction, the power of k on top is 1 less than the power of n on the bottom. K to the first, n to the second, k to the second, n to the third. We're good to go. So now we're going to pull out everything. So we're going to break this into 2 separate sums, and then we're also going to pull out the constants. So I'm going to write this as the limit as n goes to infinity of a constant times a sum, k equals 1 to n, plus another constant times a sum, k equals 1 to n. The first one, I can factor out the 100 over n squared, and we're left with k. For the second one, I can factor out the 375 over n cubed, and we're left with k squared. And then we use the formulas, right? We know that the sum from k equals 1 to n of k is n times n plus 1 over 2. And we know that the sum from k equals 1 to n of k squared is n times n plus 1 times 2n plus 1 divided by 6. Here's another good reason to use right endpoints instead of left endpoints. If you use left endpoints, this formula is the sum from k equals 1 to n of k minus 1 squared, which is just a little bit, it's similar, but it's actually not quite the same. The formula ends up being like n times, or like n minus 1 times n times 2n minus 1. It's just like, you don't want to deal with a different formula. So that's another really strong reason to use right endpoints. All right, so now we're going to take the limit of this. Okay, so I'm going to tell you real quickly, here's what the limit is. The limit is 100 divided by 2 plus 375 times 2 over 6. And you probably know how I got that, but just in case you didn't, what I'm doing here is I'm using the fact that if you multiply this out, you would get 100n squared plus some smaller terms over 2n squared. And the limit of that is 100 over 2. Similarly here, if you multiply this out, you would get 375 times 2n cubed plus some smaller terms over 6n cubed. Right? You have a 375 times n times 2n. That's your leading term. So we end up getting, let's see, 50 plus, let's see, 2 and 6 cancel, 3. 375 divided by 3 is 125. So we get 175 for the actual area under this curve. 175 square units. All right, let's take a